Hi, I'm Quentin Reeb, and today I'm going to be taking a look at two-dimensional motion in Vernier graphical analysis and video physics. So let's first take a look at the setup in a video physics, which is essentially me lobbing a very light ball, and that lightness will play a huge role later on in my explanation. But here, as we can see, the ball is actually moving in two dimensions. It's not just moving up or down or right or left, it's actually moving up, down, and right at the same time. So if we take a look at our origin, we can see that the two axes are actually placed in a way that demonstrates how the points are actually moving up and down and right at the same time. So they're moving along both axes simultaneously, which is pretty significant. It's much different from what we did in our last test. So now let's take a look at what we can see in video physics, which is going to demonstrate exactly what I'm talking about. First, let's switch it to the X so that we're not confused. As we can see here, the position versus time graph is relatively linear. It has a few discrepancies, a few wobbles, but at the same time, it is pretty darn linear, meaning that the velocity itself is going to be constant. So the position versus time graph demonstrates its slope in velocity. So let's highlight this to get the exact velocity, so I'm not just talking in generics. But here we can see that the velocity is around 2.725 meters every second. So meters per second, rather. So that means that every second the ball moves in the x component, not the y component, but the x component, an almost completely consistent rate of 2.725 meters. But now let's take a look at how that is corroborated by our velocity versus time graph, which should show relatively different results. Because, as we know, this is the real world. This isn't just some kind of vacuum that we sadly don't have access to. That would be epic, but we don't. But as we can see, the slope is actually not completely zero, as we would expect from the linear nature of our position versus time graph. Here, it's actually the acceleration is actually around negative 0.430 meters every second, which means that around every second, or not meters per second, but negative 0.430 meters per second squared, meaning that every second there's about a decrease in 0.43 meters per second in that second. So every second, that's the amount in meters per second the velocity goes down. It's very slight, but it is still pretty significant. As we can see, that's probably as a result of air resistance, which is essentially slowing down the x component velocity of our ball. But now let's take a look at the y component, which is something completely different. We're going to see that it's actually going to demonstrate something that we never expected before, or that we would have expected if we really paid close attention. I didn't expect it, at least. But here we can see that actually we're going to ignore the position versus time graph for now, but the velocity versus time graph shows something pretty linear, meaning that the acceleration is relatively uniform. Not quite, because there are a few wiggles like in our previous graph. But here, if we highlight this, we can see that we have about a decrease, or a negative speed, negative acceleration, so an acceleration of negative 7.326 meters per second squared, meaning that every second our velocity, our velocity moves in the negative direction for about 7.326 meters per second every second. So that essentially means that this is clear from the curve fit itself and even the original graph, that we're actually going to see a movement towards zero, which is corroborated again by my video physics, which essentially shows that in the y component there's actually pretty flatness, even though it's still moving in the x component, but it's pretty flat in the y component at the peak. But that is essentially only at the peak, because when it goes towards the negative infinity, it never gets there obviously, but it goes towards it, it is actually increasing in speed again. So it decreases when it goes to zero, because it's getting less positive, and then it becomes more negative after it passes zero. So that's, again, what is shown by this graph. But let's take a look at what that actually means, because this is actually not completely linear. What the fact that this is not completely linear actually means. So here we're going to see that the fact that this is not completely linear, especially if we highlight this portion right here, As you can see, that little bump there is pretty significant, which is probably, again, due to air resistance. And if we take or if we remember our velocity, or our acceleration, it was less than 9.8, which is what we would expect in a vacuum. But this is not a vacuum, this is the real world. Again, air resistance is actually slowing down even the y component acceleration here. So keep that in mind, and I hope this video helped, and I hope I get 100%. I hope this was a good explanation. Thank you so much for your time, and good